Okay, so this time I come here as a plain researcher. So actually, I was approached by Ignacy some time ago, just before elections, and he asked me to come here. And I said, okay, I don't know what to say to these guys in this conference. I am a researcher. I do research. I do research in machine learning and data science. But then, well, after all these excellent presentations about policies and research data management, what can I say to them that could be interesting? I actually measure my speeches in terms of the amount of equations I have to put in there. So in this sense, well, I had to give something that could be somehow useful for all of you. And actually, I would like to have two heads in this presentation. I will start with, and this could be the conclusions, because they are the two flavors of this presentation. So I want to share experience in openness from the machine learning and computer science community. And that's going to be one thing. And another thing is a little bit more technical. It's going to be just a sketch about proposing potential solutions to one of the drawbacks that makes researchers not wanting to share data, which is sensible data or how to address privacy issues. And in this sense, machine learning can give you something. And I'm going to give you a brief sketch of what we can offer. So let me just start with something which is the community shift. Machine learning is actually doesn't create data. It's a discipline that ingests data, create tools, build methods, algorithms that actually evolve in time based on past experience. And experience for us is data. So we don't care much about what this data comes from. What we care is much more about how its geometrical properties of data, how its layout. It has correlations in them. It's a sequence of data, is coherent, this kind of stuff. Obviously, data is crucial in machine learning because we are trying to develop algorithms that work with that. So, examples of machine learning tasks, well, you already know that, but just to make it simple for you, automatic translation or synthesis. So, for example, I don't know if you have seen this picture before. This is a Skype translator, which actually is able to, in real time, translate in 5 different languages. So you speak in Spanish, and it can translate to English, it can translate to Chinese, to German, and Italian in real time. And also it can translate written down in, I believe that it's 40 different languages. So, okay, this is something that machine learning works on. And it's basically the fact that natural language processing, you can take information, process them, and predict, or in this case, classify, understand the words they are. Other examples, this is automatic captioning. A lot of data comes in the form of images. So, okay, making things machine readable, it's not easy, definitely. And there is a huge amount of information that comes in form of images. But we start having tools for tackling these issues. And these are real automatic captionings. For example, the one on the left, it says, a little girl is eating a piece of cake. Or the one in the middle, a baseball player throwing a ball in game. Or the one on the right side, woman is holding a bunch of bananas. And this is completely automatic. So we are at this stage of technology. More examples of machine learning, business analytics. You can get predictions on finance, or you can get, I don't know, whatever. I'm sure you can figure out what we are going with this machine learning trend and data science stuff. And current machine learning focus is in terms of improving the results, on terms of accuracy, in terms of robustness, speed, interpretability. And we have to compare with other techniques, because in the end is what we want as a researchers. I'm building a new algorithm, I have some problems, this algorithm is not robust enough, so what I want is to somehow beat, if you want, or you want to improve the robustness of this algorithm with respect to the others in a big, broad amount of potential applications. This means in a big, broad amount of data sets. So you have to get data readily available, and I will have to compare with many, many machine learning or many, many data sets. It's not difficult to see some studies with around 200 different data sets when you see a publication in machine learning. Okay, but as a researcher, we pursue to contribute to advance of science. And to advance science, reproducibility is the key issue. And why reproducibility is the key issue? Because it helps to eliminate individual biases. So in this case, the researcher can have an interpretation of the data, but another researcher can have a different interpretation of the same data. And this is important, and this is what leads the advance in science. And as a researcher, I want two things. I want dissemination, so there is this reporting process, and because I need to claim authorship, because somehow people is going to evaluate me as a researcher for that, for that kind of work. Also, quality. We want research, or we want our experiments or science to be of quality, which means it has acceptance in the community. And for this reason, we use peer review and this kind of stuff. But it's also the quality of this research is one of the key performance indicators that many organizations are using. Okay? So what I would expect is that I make some experiment, I report that, and then the rest of the people is able to take this report and reproduce my experiment. So this is the reason why we use publishing, right? And we take our experiment, we get a draft, we send it to some journal, it gets to to blind review or double blind review. They give you feedback, and you give some rebuttal or address the feedback, and then it finally gets published, and you expect that this research is going to be reproducible. The problem here is that first, it's an extremely long process. It takes more than a year, so this is not a very good dissemination tool, right? Or even an attribution, right? Because more than 1 year, there are many fields that the same idea could be at the top at the same time or very hot at the same time. So, well, there is some kind of competitive aspect to that issue. On the other hand, there is the peer quality assessment, so that gives you critical feedback and try to guard against potential errors. And also, this peer quality assessment is what makes this a major source for ranking researchers are promoting. But there is one drawback, and is that non-published research is not research at all. And this is an important issue. So what to do in that case? Of course, you go to a conference. You go to a conference, which is a pair of process in terms of the amount of time you have to spend for publishing your research. Your quality assessment could be, well, in the middle, more or less, let's say in average. Still, non-published research is not research at all. But let me just focus on this NIPS case. NIPS is the Neural Information Processing Systems. It's the most important machine learning international conference. And I have titled this slide, When Conference Papers Are All News. In machine learning, 3-6 months, which is the conference cycle lifetime of a paper, is extremely large. And this was held in Barcelona last December, 5th to 10th. And I'm putting here just this conditional image, I cannot see that better. Conditional image generation with pixel CNN decoders, right? Well, actually, you can find this article in Archive 6 months ago. I actually read it 6 months ago, 6 months before. So when it was at the conference, it was all news. We all knew about that. Not only that, there were also papers citing this specific paper, and because it's a really good paper. So, which is interesting? Well, it seems that the machine learning community is starting to consider the 24/7 publishing cycle. Archive is immediate. It gives you immediate attribution. But there is a big problem, no quality assessment at all. And we have to distinguish what is good research from fraud, because anything that is published there could be taken for granted, because it's a publication in the end. And we still have this mindset of any publication is the essential truth, right? Well, however, in reality, publication doesn't give you reproducible research. In the best case scenario in which you are publishing in a journal and peer reviews are very strict, well, it could be more or less reproducible. The algorithms you expect to be more or less reproducible and so on. In the conference, maybe there are some other hidden information, and in archive, you don't really know what you will find. So obviously, data is important for reproducibility. Because if you're given the data and you're given the document, then, well, probably you will be able to reproduce the same results and discuss about it and make science advance. Well, one of these examples is PLOS ONE, which I was editor also some time ago, that focus a little bit less on the breaking if it advances or if it's a really novel proposal, but focus more on methodological correctness and data sharing. So one of the policies of PLOS ONE, you already know, is the fact that they require data to be shared. But in machine learning, you need a lot of data sets. So how do we validate that an algorithm actually works? Because I have to compare them. So we use different repositories. We have several repositories. In this case, this is a University of California Irvine repository. This is one of the oldest repository that is used in machine learning. This dates back from I don't remember when. Before my thesis, there was this repository, right? And it has thousands of data available there. And let's focus just on one of them. For example, this is Facebook metrics dataset. And this dataset, well, oops, sorry about that. I just pushed the cable. So this dataset, or in that website, what you will see is that it comes with different information. First, it describes the dataset. What are the attributes that you have? It also tells you about how to cite this data set. So anybody using this data will know and will get credit for the effort for doing the data set. And also, and all publications will share the same citation. Okay, so I think more or less we are on it again. Okay, and this is another one. This is another repository. This is the machineLearningData.org, which also allows you to query for different data sets. You can query in terms of the data set. you can query in terms of the material and methods. So for example, let's say that I want to use principal component analysis, which is a standard tool for dimensionality reduction or whatever thing. You can query by technique. And then what are the data sets that people trying to compare or working on that subject are using. You can query for learning tasks, and you can query for challenges. Okay? So, okay, data is important. But data is not even enough. I'm just bringing you the attention to this US Security and Exchange Commission that this was a proposal in 2010 with respect to the financial crisis that actually tell that all financial products, besides the huge amount of information you are giving to the banking or to the security agency, should provide Python code so that they can somehow make their own simulations about how harmful or if the claims they were saying are okay. So, data is not enough. You need code, definitely. Because in the end, we are writing down algorithms, we are writing down ways of processing data, and, well, there could be something lost in this process. So we can share code, and obviously one way of sharing code is GitHub, as Daniel showed us also with his presentation. Still, even if we have code, I still believe it's not enough, because the devil is in details. You have the manuscript, you have the data, you have the code, but then how did you deal with those missing data? Did you remove a couple of records because they were outliers? Did you normalize the database? There are many things that you are doing to the data that you don't have space in experimental settings to describe, or probably some of them are so obvious or so, let's say, not relevant that you don't put that. So, and this, again, hinders the process of reproducibility. So you need something else. What else? And I put here just a potential, one of them, many potential solutions. These are Jupyter notebooks. And Jupyter notebooks is precisely a tool that allows to put inside executable code, LaTeX if you want to write down equations, Markdown, HTML and CSS, hyperlinks, embedded frames, and all this kind of stuff. In this site, you have one of my lectures in machine learning, which has here on the top some code, which is written in Python, and actually I can execute that live in front of my students if I want. You have the results with very nice figures and this kind of stuff. You also have LaTeX, so you can write down equations in a nice way, and you can also put here some CSS style if you want to make things and this kind of stuff. So most probably, this is the way we have to share science. We are not sharing data, we are not sharing documents, we are not sharing just code, we are sharing experiments. And experiments is all of that. And there are some repositories that actually put them together. Gitshift. Gitshift is GitHub plus archive. So what you get is, this is the article, this is the archive, this is the GitHub, these are the links. So you can get all that, you can reproduce and get the tables on that particular article. Then you say, okay, this is great, because it allows me to assess that what you're saying is correct. Or if I have some other interpretation, I can share that this is advancing science, in my opinion. So, bottom line, science is more than a publication. At its core lies reproducibility, which involves data. But this is not even enough. Code and precise experiment reproducibility is at the core. But this means that data and programming literacy is needed. So this is going to be this bottom line. I don't know how much time I have, because I have quite a lot of things to say still. Something else. Sorry. Something else. About quality assessment, let me just put this example of open review case. This is ICLR 2017, so 2017. This is the conference on deep learning, which is going to be held in the next month. These are the rules for submitting to this conference. Submissions are posted on Archive. Submissions are posted on Archive before being submitted to the conference. Program committees assign blind reviewers, as always. Anyone can ask program chairs for permission to become an anonymous designated reviewer, so there is an open bidding process. Open commenters will have to use their real names. So this means that at the moment the submission is made, this is open to everyone. And it actually means that anyone can comment on that. Not only comment on the article, but comment on the review, which is great. And papers that are presented in the workshop track or are not accepted will be considered not archived. So you're free to submit them everywhere else. But the article is still there. And you can see all the versions, you can see all the feedback, and you can also see, for example, actually, the feedback is an extremely important thing because sometimes people or PhD students spend a lot of time trying to figure out what does a correct experiment means. And you obtain that value after submitting many times and having a lot of reviewers saying this is not good, you have to do that otherwise. In this case, you are seeing lots, this is probably the largest database for open reviews ever. So you go through some of those articles, and what you will see is what people expect from an article in this particular conference. But not only people, I mean reviewers, the rest, the peer researchers. Rejected papers have influence, because you can see some rejected papers there. You can see there could be good ideas. There could be that there still needs some polishing. Authorship is still claimed. So that's interesting. It's not also very nice because it in the end can become a popularity contest in the sense of I can ask some of my friends to actually say, please review my article and review it well and this kind of stuff. So we have to be cautious with that. But this is, I think I wanted to share this open review because I think that there is some interesting points that we can learn about. So let me just take a different hat now, and I want to take a hat of lecturer, just in a small bit. So this is the technical and boring part, in which I'm going to talk about deep learning and this kind of stuff. But I hope you actually bear with it. So one of the problems of sharing data, if this data is sensible, is the fact that, well, precisely that, it's sensible, or you can have some privacy issues. So in order to address that, you can use many different algorithms like k-anonymity or differential privacy or whatever. And the idea is, okay, I have my records, and I aggregate them so that I cannot go back and recover the identity of the original records, and I can share that thing. Well, still, even if you do that, there are ways of somehow undisclosing this kind of strategies. And for example, this is from the point of view of differential privacy. This was an experiment that wanted to assess. It was about predicting the dose of warfarin. The warfarin is a drug for avoiding blood clot, I believe. And this is the privacy budget, you can see on the upside, against the relative mortality if I had administered the dose I predicted. So the idea is, okay, I give you data. This data is anonymized, and I want to use them for predicting the dose of warfarin given a new patient. So obviously, the less private you have the data, obviously, this is relative mortality, so this 0 here means that it actually is exactly the same performance as full disclosure. But the more and more you're putting private issues, the mortality, the expected mortality increases up to 30%. So the disclosure risk is obviously this thing. Okay, you can be very protective, but then probably your data is not useful. And you can be less protective, but then your data has more predictive power, and in this case, which is about mortality, then reduce the risk. And this is a big issue. So let me just briefly say how machine learning works and how deep learning can help us to address this issue. So this is the classic machine learning pipeline. There is one guy, this is the data scientist, the machine learning practitioner, whatever, that has some data and actually think about how to describe this data in machine-readable format somehow, or in a vector of numbers. For example, okay, some descriptors, some attributes, which I give to my predictor or classifier of things, and it's going to assess if, okay, it's okay or it's not okay. And actually, we can think about removing this machine learning practitioner, and instead of that, making it fully automatic. So if we can create a learner, automatic learner, in which I give the data, and actually get some kind of intermediate representation so that the classifier understands, we can actually get exactly the same result. Note that this intermediate representation doesn't necessarily need to be human comprehensive. So, what if the learner and classifier are one thing? Well, this is what deep learning is about, this box. And if we open this box, what we see inside is a very good old friend of the machine learning community, which is neural networks, standard neural networks, nothing really fancy. So now think about this problem. This is a really interesting problem. We have this deep learning white box there. We have data on the left side. And now let me just go and say, okay, I put the data and I get the same data. This, okay, awesome. Awesome, this doesn't work at all. Okay, let's see what's going on inside. But what we see inside is, again, this same neural network. But if we look at it with a little bit of caution, we see that there is a bottleneck in the middle. So my data, which has some representation, I want somehow to compress that data. And from this compression, then I want to decompress. So I get the same data back. Okay? So we can see that precisely as that. I take my data, I create some intermediate representation, which is non-human readable. And I take this non-human readable representation, which I can put back using this decoder strategy. Well, I can get rid of this particular second part, and what I have is an extremely good encoder with the following property. The property that I take the data, I put the encoder, I pass it through the network, and actually what I get is something that even in my non-readable or interpretable representation is still very good for classification and task-specific purposes. So it actually means I have one record of one patient, and this is actually being done also for predicting 80 different kinds of illnesses with actual patient records. And you can actually predict them exactly with the same accuracy as if you get the original record. But it's completely irreversible, non-reversible. So this data, you cannot get back the original representation, except if you have this second part. Well, and there is another thing, because, okay, people who is very knowledgeable about differential privacy will know how to query my database and actually say, okay, yes, but I do it in such a way that I can get a little bit the way of how you are encoding this thing. Well, this is a nice property which was conceived in the deep learning world as a drawback, but I believe that it's extremely good opportunity, and it's the fact that this is an optimization process, but this data, you can get the same data through the same network and get two different representations with exactly the same power, representing exactly the same data point or data record. So this actually means if there is some guy trying to figure out or to break into your database and go over privacy issues, you can change representation completely without losing the task-specific power. So, and this is, for me, it's very important because it gives you the possibility of sharing at record level data. So, conclusions. First, research is based on reproducibility, and this means documentation, data, code, and details. And finally, machine learning methods can help in the challenge for democratizing data. And that's all. Thank you very much.
Thanks, Oriol, for the talk and for the class. Is there any question, maybe for the talk?
Thank you. I felt as I was in a master class. Thank you very much.
Sorry about that.
No, thank you. My question is about, is something specific in your area? You belong to the math community or physics, both. I'm not really sure. I'm not more or less about that. You know that you have archive since 20 years before,
yeah,
or more.
Yeah,
so
it's
nothing new. What makes the difference? Why people in physics, why people in math are so advanced, and why other disciplines couldn't do the same? What are the interests? What are the different kinds of perspective or kind of the different ways of doing or performing science? Have you ever talked about that with different communities, with different research communities other than mathematicians and physics? Because you are ahead, several years ahead of the others. So it's something different. Even in the way that publishers manage the journals, if they are for different kinds of the communities. You are in physics. You are in. As I am a librarian, I have to validate different papers to be open. It's very different cases if you are in physics or if you are in medicine, for example. Nothing like that at all.
Well, there are certainly there are differences in the communities, and what I share here is not for all the machine learning community. It's for a specific subfield in the machine learning community, which is moving extremely fast, which is the deep learning community. The reason for that, I believe, is a combination of different things. First, big stakeholders pursuing big companies pursuing to hire very knowledgeable scientists in this field. It's like Google, Facebook, and all these guys. And there is also the fact that lead researchers actually embrace that and said, for example, all high-standing researchers actually start publishing like that. And the way for communicating with the community was not even archive, was Twitter. And actually, if you want to know about deep learning, what you should do is to go into Twitter and actually see what's going on. Otherwise, you cannot keep track of what's going on. Because actually, navigating archive is madness. There's so many things inside. Even there are many, I wanted also to share some recommendation tools, some recommender tools that has been done for managing and making articles in archive for sanity preserving issues. I mean, so I believe that these are the two drive that makes probably this community a little bit, okay, we need people to be working very fast because it has business value somehow. Still, that's the way I believe it should go. But this, on the other hand, has a trade-off, because I have my PhD students, and I want them to be successful and to be hired and to have a professional career, and they are nowadays being evaluated using first quartile publications and this kind of stuff. And okay, I can say to my PhD students, okay, go full open, because I believe in full open. Well, I can do full open. I can do, because, okay, I care about, but I care more about science, but they care about their position, right? So I can say to my PhD students, go full open, but then you're not going to get hired, you're not going to get a position at the university, but then, okay, this is tough. You have an ethic dilemma there. Advance science or care for people. So this, I was actually gladly impressed by the fact that there is people actually trying to figure out alternative metrics to take that into account, because I believe that's key. That's key at national level. If we need habilitations or promotions at national level, and we also need openness at national level, we need both policies to be aligned. And this is not happening now. One pushes in to one direction and the other in just the opposite. And that's what's driving most of people. Data has value in itself. Conserving data and not sharing data has value right now. So that's the thing that we have to break. But this means rankings, incentives, what Eva said, has to be pushed from the top.
Any other question? No? So, oh, Daniel.
It's not really a question, it's a set of questions. So, since I didn't have the privilege to talk after you. So, at first, a brief comment on your question. So, in biology and medicine specifically, there is now an effort to actually bring preprints to life. It's called ASAP Bio, ASAP for as soon as possible. And it has support from NIH and Wellcome and a number of other funders. And we are at the stage where we're really talking details about technical implementation of infrastructure for actually sharing preprints and how to recognize when people have shared preprints, how to introduce that into evaluation workflows. And this discussion of having it in the life science has actually triggered the chemistry community to do something similar. And now there is a number of communities that are doing this. And all of them always look to archive and the, let's say, equation-focused fields because they are leading. Second, I liked it that you contradicted yourself in a very nice way. So let me explain. Initially, you said, well, machine learning just consumes data and doesn't produce data. And then in the end, you said, well, but we should share all of this in things like Jupyter notebooks, which in a sense are actually data. The point here being that whatever you're doing, whatever you're producing should be shared. And sometimes the focus is more on data, sometimes the focus is more on code, but even code could be the data for someone else who, for instance, studies how different algorithms are implemented in different contexts and things like that. And so, nobody should say they don't produce data. They are producing something, and if it's of value to them, it might well be of value to someone else. And as a biophysicist, this reminds me of a let's say, a conversation or discussion that we've had also as students. The experimental biophysicists, they always said, yeah, well, we have no incentive to share the data because we don't know who's going to do what with it. And the theoretical biophysicist said, well, we can't work without data being shared. But if everybody shares their output, like if the experimentalists can actually use your machine learning tools to improve their own experimental research, then they have an incentive to share their own data. They understand that they're contributing to the system. And that's why it's so important to talk about those interoperability aspects and so on, to have the systems that actually work. So not that something just sits somewhere in a repository, lonely, but that it is a component of workflows of people other than those who have produced whatever it is. So yeah. Sorry for the long comment, but it was a very stimulating talk.
Appreciate it all. And actually, you're completely right in the sense that effectively, when I'm saying sharing details and sharing code is actually data, well, then we have to think about data as something bigger than just the actual measurements that coming out from experiments. It's something else. It's also the publication, it's also the code, it's also the details, it's the Jupyter notebook or whatever. That's also the data in that sense. Yeah, definitely. Appreciate your comment.
Okay, so thank you, Oriol, again for your talk and to be with us.